This unit begins with a focus on continuous probability functions. Two such functions are shown on the slide. Here are a few facts about continuous probability distributions. In a probability distribution, the area under the graph is 1.0 or 100%. If an event occurs, the probability of that event depends on the interval in which the event occurs. In the graphs, the probability intervals are indicated by the space between the x1 and x2 points. Depending on the circumstance, the interval can be very large or very small. We won't spend much time on the uniform probability distribution, other than to develop a brief explanation of it. If the probability distribution takes on the form of a rectangle, it defines a uniform probability distribution. Here is an example. Let's roll a die. If it's a fair die, the chances of rolling any number from 1 to 6 is 1/6, or 1 in 6. Therefore, it forms a uniform probability distribution. The chances are 100% that I will get a number between 1 and 6. The chances that I will get a number of 1 or 2 are 1 in 3, or 33.33%. The key is that the probability in any interval along the continuum x is the same as any other interval along the continuum. This will not be true for the normal distribution, as we shall see shortly. We begin our discussion of inferential statistics with a look at the fundamental building block of this classification, namely the normal probability distribution. Sampling, confidence intervals, hypothesis testing, and fundamental regression all use this concept, so it is important to develop a basic understanding of a normal probability distribution. The normal probability distribution is a continuous distribution over a relevant range. By continuous, we mean that the distribution contains all possible values between the extremes so that a continuous line can be drawn depicting the distribution of occurrences from one extreme to the other. Here are a few examples of random variables that are normally distributed: heights of people, scientific measurements, test scores, and amounts of rainfall. As you can see, there are a variety of normal probability distributions that we encounter every day. Let's look at the characteristics of a normal probability distribution. You will note that the distribution is, in fact, continuous along the range of x. We see the bell shape of the distribution, and the distribution is symmetrical. This means that if we folded the curve in half at the point of the mean, we could overlay the lower half of the curve with the upper half of the curve exactly. This is a critical point because this will enable us to make some important calculations in determining the area under the curve. We can define all normal probability distributions in terms of its mean, which is identified by the Greek letter mu, and by the standard deviation, which is defined by the Greek letter sigma. Note that these are population parameters. The highest point of the normal curve is at the mean, which is also the median and the mode for each of these normal distributions. As you can see as this graph unfolds, the mean of any normal distribution of a random variable can be any value, positive, negative, or 0. Let's consider the standard deviation of normal probability curves. As the standard deviation gets larger, the curve gets wider and fatter. As the standard deviation gets smaller, the curve will grow taller and more narrow. This should make sense since a large deviation about the mean requires that the observations be spread over a larger array of x values, and a small deviation indicates a small spread around the mean. Finally, we note that the probabilities for the normal random variable are found in the area under the curve. Note that the total value of the area under the curve is 1.0 or 100%. Since the curve is symmetrical, if we bisect the curve at the mean, 0.5 or 50% of the curve is below or to the left of the mean, and 0.5 or 50% of the curve is above or to the right of the mean. In the last unit, we introduced the empirical rule and gave some general guidelines for the distribution of the data values within 1, 2, and 3 standard deviations about the mean. A graphical representation will help our understanding. You see the normal curve. First, we'll bring in 1 standard deviation from the mean. That encompasses 68.26% of all the values within the curve. In other words, there is 34.13% of the values between the mean and 1 standard deviation above and 1 standard deviation below the mean. Next, let's introduce the 2nd standard deviation, which takes our overall area covered up to 95.44%. And finally, we see the 3rd standard deviation, and we now have 99.72% of the curve covered. The remaining areas in the 2 tails of the distribution represent extremely rare values. There is a special case of a normal probability distribution that is called the standard normal probability distribution. The standard normal probability distribution is a distribution that is defined as having a mean of 0 and a standard deviation of 1. Here is a view of the standard normal probability distribution with a mean of 0 and a standard deviation of 1. We call the standard normal probability distribution the Z distribution. You can convert any normal distribution to a standard normal distribution by applying the standard score formula from Unit 2. Let's take a look at it. Here is the formula for determining the value of Z. Z is defined as x minus mu divided by the standard deviation, or the difference between the value of the variable x and the population parameter mean mu divided by the standard deviation sigma. The calculation of Z tells us how many standard deviations the variable x is from the population mean. Here is an example. The semi-monthly salaries of recent MBA graduates follows the normal distribution, with a mean of $2,000 and a standard deviation of $200. What is the value of a salary of $2,200? Our population mean is $2,000, our population standard deviation is $200, and our X value is $2,200. So employing our formula, $2,200 minus $2,000, then dividing by $200 gives a Z-score of 1. We are 1 standard deviation above the mean of recent MBA graduates. In Excel, you can use the standardized function to compute this value. Given the properties of the standard normal curve, we know that 34.13% of the values in the distribution are between the mean and 1 standard deviation above the mean. We also know that 50% of the values are below the mean. Thus, we know that 84.13% of the recent graduates earn $2,200 or less semi-monthly, and 1 minus 84.13% or 15.87% earn more than $2,200 semi-monthly. There are 2 functions in Excel that make computing probabilities under the standard normal curve and Z-scores an easy task. They are norms DISD and norms INV. Both functions apply to the standard normal curve, which has a mean of 0 and a standard deviation of 1. The S in the name of each function reminds us that these 2 functions apply to the standard normal curve. Next, I'll demonstrate these 2 functions in Excel.